Would you agree an infinite sum is like a limit? Okay, so are derivatives preserved by limits? You think? No. In fact, here, these derivatives, you can see, are starting to behave very wildly, and their limit, limiting derivative of the limit is 0. This is not in general true. What about derivatives? What about integrals? So think of areas. Are they preserved by pointwise limits? No. Example 3. Does not. This notion of limit is actually it's not such a. It doesn't have nice properties, does it? With respect to a lot of the things we care about. So this points out the fact that we actually need a stronger notion then to help us. That it will maybe help some of our issues here. Okay, not all of our issues, but some of our issues. And exactly what issues they'll help with is I'm going to leave to much to analysis 2, Math 132. But let's look at a stronger notion. Let's look at the supremum norm of a function, which is defined to be, tell me the function value and take its supremum at all points in the domain of the function. Okay, so let's take its supremum of the absolute value. Okay. Okay, so for instance, the sup of this function would be what? 1. The sup of this function over the entire domain? Yeah, infinite. Yeah, we don't like that, okay? If I restricted my domain, you could see the function would actually have a supremum. Okay? Okay. So, interesting. Well, let's make a definition. So the definition will be a different kind of convergence, and it's called uniform convergence. Not to be confused with uniform continuity. Completely different concept. But the word uniform is supposed to make us think of what? Well, everybody's wearing the same uniform, right? Okay. So what is that? What's behaving uniformly here? We're going to say f of n converges to f uniformly, and I'll put a little u over the arrow. And we'll say f converges uniformly to fn converges uniformly to f on E if for all epsilon bigger than 0 there exists an n such that little n bigger than big N implies the norm of fn minus f is less than epsilon. Okay, so question. How is this like or different than the notion of convergence, the notions of convergence you've seen before? Katie?
It preserves the peaks, like on example 3, it preserves the fact that there's a peak there, so you can't just ignore that the function does something weird, even if it does it for a small amount of time.
Okay, we'll come to this example in a second, but I think what you're saying is this sequence would not converge to 0 uniformly. What's uniform about this definition? Give you a hint, I'm taking a supremum here of differences. How is this definition different than pointwise limits, which also ask you to take a limit of a sequence? Jenny?
You're saying that all points in F have to be close to all points after a certain point, as opposed to, if you in example 1, they all eventually go to 0, but some are still really, really far away from 0 at each step.
Excellent. So the idea here, because we're looking at the supremum of a difference, and we're demanding that be less than epsilon, is we're going to have ribbon convergence. So this is the way I like to think about it. You're trying to, so you can draw an epsilon ribbon about the limit f and fn is eventually stays in the ribbon. What's uniform is it's the same n works for every x. The same n works for all x in E. Okay. Okay. So just to look at our example here, let's draw a little ribbon and see what happens. Suppose I draw, so would you say that this sequence converges uniformly to the limit? No. These functions are not all living in the ribbon eventually. In fact, every single function eventually leaves this ribbon. Yes? Epsilon ribbon. Okay. Does this function converge uniformly? This sequence converge uniformly? No. Yeah, you'll have problems still no matter how far you go. You'll have problems where this function does not live completely inside, right? Okay. What about this sequence? No, doesn't converge uniformly. What about this one? Oh, yes, this one does. Okay. So not all our problems are going to be solved by this notion of ribbon convergence, uniform convergence. Okay. In particular, you'll see not all of them will be solved, but maybe some of them will be. That's the question. Now, the thing you should notice about this is I've really just disguised this, but really what I've just done is I've placed all the functions in their own metric space. And I've given the distance in the metric space of functions to be basically a supremum distance, right? So this is just convergence, is just the usual convergence in the metric space, which I'll call C sub B of E. This is the continuous bounded functions on E. The C stands for continuous. The B stands for bounded functions on E, real valued functions on E. So really, isn't this just the metric, the distance between f and f? I'm just letting it be the distance between f and g to be the norm of their difference, f minus g. Okay. So, what's so great about this metric space? It's a metric space, right? What's cool? That's what's great about it. It's a metric space. Look, there are points in here. There's f1, f2, f3. I'm thinking about every function as a point in its own space. Yay. Okay, yes. Well, yeah, so certainly you could define this notion, if you like, on larger spaces of functions, but this is one class of spaces where it's convenient. Okay, you could certainly define on larger spaces. You'll have a problem defining the notion of the supremum on functions that aren't bounded, but certainly you could define it on something that's maybe not continuous. Okay, points in their own space. Question, well, okay, so uniform convergence is